Hello, Chem 1110 students. We're starting on Chapter 9, which is all about chemical reactions in aqueous solutions. Now, this is a very large chapter, and so I've just put a slide in here to give you a flavor of how much work we're looking at, because these are chemical reactions in aqueous solutions, and in fact, most reactions we're going to deal with do occur in aqueous solutions. So there's some real major reaction types we're going to look at. We're going to look at precipitation reactions, acid-base reactions, and that's going to include titrations and the pH scale, and then oxidation reduction reactions. And with this, we have to learn how to balance redox reactions. It's done differently than the kind we did last chapter. We're going to learn how to predict whether a redox reaction will occur or not. And then we're going to look at some of the different kinds of redox reactions, which include combination, decomposition, and combustion reactions. And then for good measure, we're going to look at solutions a little bit, basically talking about concentrations, like molarity and how we actually can do calculations with it, and then serial dilution, or diluting a solution one time after the next so that we get a set of solutions of a known concentration. All right, so we're going to look at some general properties of aqueous solutions. And just so that we have our vocabulary down, a solution is a homogeneous mixture of two or more substances. The substance that's in the largest amount is referred to as the solvent, and in aqueous solutions that's going to be water. The other substances that are in the water or in that solvent are called the solutes. So one of the things you need to be aware of is what we mean by solubility. And so if a substance dissolves in a particular solvent, and in this case it's going to be water, then we say it is soluble. So as far as this chapter is concerned, a solution is going to refer to aqueous, which means the solvent is going to be water. And the first thing we need to talk about are electrolytes and non-electrolytes, and we've used this term a little bit. We've never really defined it. An electrolyte is a substance that dissolves in water, and it produces a solution that conducts electricity. So if you put salt in water, you get sodium ions and chloride ions, and we say that that electrolyte has dissociated, is broken into pieces. Now, if we had a molecule that produced ions, then we would say that is ionization. So it's not quite the same as an electrolyte just coming apart in water. But if you had a setup such as what's shown in this picture, you have a light bulb with screwed into a tester that has two electrodes hanging down in the solution. And if there are enough ions to conduct the electricity, you can see in the enlarged view there, everything going to the left is going to one electrode, and everything going to the right is going to the negative electrode, and that's how the electricity is being conducted and causing the light bulb to light up. So there are also, if there's electrolytes, there's obviously non-electrolytes, and so these are things that can dissolve in water, but they do not conduct electricity. And we have an example here of sucrose, or regular sugar. It can go into water solution, as we know if you've ever put sugar into tea or coffee. And yet the molecules remain as molecules, and they don't dissociate, they don't come apart. And so therefore if you use the same setup to test for electrical conductivity, you see the bulb doesn't light up because the electricity is not carried through the solution. All right, so there are electrolytes that are known to be strong electrolytes. They completely dissociate. They're water-soluble ionic compounds, and salt would be one of those. And also strong acids like HCl or strong base like sodium hydroxide. If you have those in solution, you get a bright bulb. And in fact, we have a table here that lists 7 strong acids, and you need to know these because then you'll know that these solutions would indeed conduct electricity. All right, so now we're going to talk about a weak electrolyte. And so this is a compound that produces some ions when it's put into solution, but most of it doesn't dissociate, and so most of it is still exists as a molecule. And an example would be a weak acid such as acetic acid, which is vinegar. So you'll note that we have a new kind of notation here. We have this double-headed arrow, or 2 arrows pointing in opposite directions. And by using that, we know that there is still molecule there. It's not all broken up. And the example of a weak base is ammonia. And so once again, some of it produces ions, but not all of it. And so if you put these in our electrolyte tester, what you get is a little bit of glow from the light bulb, but not very much electricity is being conducted. So it's not a bright bulb. And so we're going to talk a little bit here about equilibrium, and we'll do more of that in future chapters. But this double-headed arrow denotes that the reaction can go in either direction. And so I have an example. This is that ammonia reaction, but with ball and stick representations for ammonia and water. And so the ammonia takes a hydrogen off the water and produces NH4 plus and OH minus. But in fact, it can go the opposite direction and create more ammonia and back to water. And so when a reaction can go both directions, we call that dynamic chemical equilibrium. So it comes to a place of rest, but on a microscopic scale, that reaction is still going forward and backwards. This is just a little chart to help you determine what's a strong electrolyte and what's a weak electrolyte. And you can see it asks questions about whether something is an acid or a base and whether it's listed as one of those strong acids. So you really do need to know those to be able to do these kinds of problems. All right, so here is an example kind of problem you might see talking about the ingredients of a sports drink, and you're asked to classify each of these as a non-electrolyte, a weak electrolyte, or a strong electrolyte, and we'll talk about that more in the future. But this leads to an important topic, and that is precipitation reactions. So precipitation reactions occur when you have ions in solution that will react together and create an insoluble product, and that's called a precipitate. In a chemical reaction in which a precipitate forms is called a precipitation reaction. And there's a picture here. The solution in the beaker sitting on the tabletop is sodium nitrate, an aqueous solution, and the gloved hand is pouring a solution of sodium iodide into it. And you see that when it occurs, or when they're mixed, you get a yellow precipitate, which happens to be lead iodide, and it will actually fall to the bottom of the beaker, and hence the term precipitate, just like rain falling out of the sky. The other ions are still there, but they're in solution. So that would be the sodium from the sodium iodide and the nitrate ion from the lead nitrate. And so here's your reaction written out. So one of the things that's really important to know is what is soluble and what is not. And of course, we've covered this before, but it's just a little review. Water is a good solvent. It's often called the universal solvent, and that's because it's a polar molecule. And it's polar because that oxygen is much more electronegative than the hydrogen, and it pulls the electrons towards itself, giving it a partially negative charge compared to the hydrogen, and we just have a nice little diagram of that. Okay, so how do ions dissolve? When you put salt into a glass of water and you stir it, what's actually happening? Well, the water molecules are going to line up so that and if you look at that negative charge, that the waters line up so the hydrogens that have a slight positive charge line up towards that negative charge and they surround it. Same thing with the positive charge, and by surrounding them, they pull them apart. Now here is a list of solubility guidelines, and once again, these are some rules that you just need to memorize. You know, which things are soluble and which are not. So on the left, they've got water-soluble compounds, anything that's got lithium plus, sodium plus, potassium plus, etc. Those are going to be soluble compounds with nitrate and acetate and chlorate. But when you get down to the chloride, bromide, and iodide, there's some exceptions. So a chloride, bromide, or iodide with silver, mercury, or lead is going to be a solid. So you need to learn those. All right, so then working off that, here is a little problem where you would say whether silver nitrate, calcium sulfate, and potassium carbonate are soluble or not in water. All right, so we're going to look at these ionic equations so we know how to write these. And so if you had a reaction of sodium sulfate and barium hydroxide, you get a precipitate. You can see because the barium sulfate has an indication that it's a solid. So if you break these apart, any of them that would dissolve, like the sodium sulfate, you actually get a sodium ion, a positive sodium ion, and negative sulfate. So when you write it all out, this is what it looks like. And what we're moving towards is writing net ionic equations, just looking at the ions that matter. The ones that appear on both sides are called spectator ions. So we immediately can cross out the sodiums and the hydroxides that were in that previous reaction. And so this becomes our net ionic equation. So it tells us the parts that are actually reacting. So here's a list of sort of directions on how to determine molecular ionic and net ionic equations. And if all of your ions are spectator ions, then no reaction takes place at all. And then here's another example we will talk about further later on. And now we're ready to go on to the next part of Chapter 9.